Okay, good evening again, and welcome to this new lecture. Today, today we're going to continue what we started last time, the addressing modes of HCS12. But first, let me just show you the note I sent you about homework. Okay, okay. In the class web page or on the e-learning, it is under lab assignments and homeworks, homework 1. So 2 sets of question exercises in the textbook, any 5 of your choice from the first set, any 5 from the second set. We have a week for that. Last time, we were talking about the instruction, the addressing modes of the HCS12, and we said addressing modes are how to access the operands that the opcode is going to perform its operation on in memory. There are a lot of addressing modes that HCS12 supports. We covered the inherent mode, where there's no operand outside of the instruction. The immediate mode, where we provided directly the operand right after the instruction, which means it is in the program memory, comes right after the opcode. And we talked about the direct addressing mode, where we directly provide the address of the memory location where the operand is at. The difference between direct and immediate, in immediate we use this the number sign to indicate that the following number is the operand itself. It's not an address pointing to the operand. The extended direct mode, we provide an address just like the direct addressing mode, but here we give it the full 16-bit address, while the indirect we give it the lower 8-bit of the address, and the higher 8-bit in this case are assumed to be zeros. And we talked about the relative addressing mode, and that this addressing mode is used only with branch instructions, where you control the program counter to go point somewhere in the program memory before or after the current location it's pointing at. Then I think we ended here at the indexed addressing mode. Okay, so let me continue from here, the index addressing mode. And swap, then I want to hide this view. Okay. In this addressing mode, the indexed addressing mode, from its name, it is clear that an index register will be used to point to the operand. So the index registers we have, an index register is any register that can hold an address, a 16-bit address. And please don't forget to write your name and ID in the chat. So any register that can hold a 16-bit address is an index register. So we know that the X and Y are general purpose index registers, that we can make them point to any place in the data memory, in the SRAM, right? In the SRAM, data memory. The program counter holds an address, but it holds an address pointing to the next instruction to be executed in the program memory. But it points to memory. Okay. The stack pointer is also a register that points to memory, to the top of stack, a dedicated space in the data memory. So also points to the SRAM. What is a stack? How does it work? How is the stack pointer different than X and Y? This has a separate lecture or part of a lecture to talk about the stack. Okay, plus and offset. So in this addressing mode, we tell the instruction, the machine code, we tell the processor that our number that we want to add, that I want to add to a register, to register D مثلا, or add accumulator A. In the past, we either used an immediate number. We just say add hexadecimal 11 مثلا, it adds it to what's in accumulator A, immediate. If you don't try this number sign, it will go to address 110011 and get what's in here and add it to what's in A. Okay, so either we provided the operand or the address. Now I want to make X point to somewhere in memory and tell the instruction that the operand that we're going to add is in the memory location that X is pointing it to, or Y, or stack pointer, or program counter, plus an offset, maybe X or X plus 3 مثلا here. So add this one. How do we do this? We'll look at some examples. But in general, we make an index register, one of these 4 registers, hold an address, and then we tell the instruction that our operand is at the memory location that is provided in one of these registers, plus an offset. The offset can be a 5-bit number, يعني a number that is up to 2 to the 5, which is what? 2 to the 5 is 32, yes. 32 يعني من minus 16 to plus 15, صح? يعني you can tell it that if you use a 5-bit offset, then you can say that my operand is at the memory location that is pointed to by X plus up 15, يعني بعديها 15 locations. This is my operand, or before it 15 locations upward. Okay, the offset can also be 9-bit number. 9-bit number يعني can go from minus يعني 9-bit كأنه يعني signed 8-bit صح؟ So from minus 256 to plus 255, or a 16-bit number, 2 to the 16 minus 64k to minus 32k to plus 32k. ماشي. These modes can be used with something called pre or post decrement or increment. We're going to look at all these things. The offset also can be in a register, not a separate number. We're going to look at these. So let's see an example. Load accumulator A. Instruction load accumulator A. شوف بالأول in the first previous examples. Load accumulator A مثلا here. We gave it the number directly, 55. Here, it's going to put 55, right? Hexadecimal, right in A. Well, it's going to add it to A and store the result in A. Load, sorry, it's not an add, load. Okay, so it just puts the 55. Here, it's going to load the number in memory location, address 0020, get this number and put it in A. In A. Here is different. Here, it's different. It's gonna go to the memory location. مثلا, let's assume that X is equal to 2000. مثلا. Okay. This instruction is telling the CPU to go. So X is pointing here. إذا هذا طيب ليش أنا بخربش هون؟ if this memory location is 2000, then X is pointing here. This is 2000. So I'm telling the processor to go load the number in x plus 4. Yani x is 2000, x plus 1 is 2001, plus 2, 2002, 2003, and 2004. So this is plus 1, 2, 3, 4. So the operand over here is going to be loaded to A. Not the one pointed to by x. No, x plus 4. This is the offset. طبعا, if you want the one that is in the location pointed to by x, you can have the offset be 0. Yani, as easy as that. صح? So load accumulator A 0, x, it will load this location at address 2000. تمام؟
دكتور يعني هون الفور هي الاوفست صح؟
Again, what the 4 is the offset. Yes, 4. This one, يعني okay, sorry.
يعني هي هون 4 بايتس.
No, 4 locations. It's an offset to the address.
اوكي لانه بالسلايد اللي قبله حكيت ممكن تكون 4 بت 5 بت 9 بت.
In this case, what's the size of the offset? 5 bits, صح? Because it's a number between minus 16 and plus 15. صح؟ لأن in this case it's 5. This is the offset.
تمام.
ماشي؟ You add it to x. So x is 2000. So 2000 plus 4. يعني the new address where you're gonna go fetch your operand from is 2004. تمام? And again, if you don't provide the number sign here, then you're talking decimal. ماشي? So when the offset here was 4, it didn't make a difference. But if it is 10, 10 is not the same as $10, right? 10 is equivalent to $A. ماشي? So you need to make sure that, or remember, if you don't use the $, you're dealing with decimal numbers, not hexadecimal numbers. Okay. Store accumulator B at memory location Y minus 8. Y minus store accumulator B. So if I go here, let me go here. So this is the memory location. Store accumulator B at minus 3, comma Y. Y is a register, index register that can hold an address, 16-bit address. Let's say it is 3000. Then Y, let's assume Y is pointing, this is address 3000. Y is pointing here. Then I'm going to store accumulator B. What's in B? Whatever B was مثلا 22 hex. Okay. Y minus 1, Y minus 2, Y minus 1 is $2FFF, minus 1 is, sorry, minus 2 is 2FFE, and minus 3 is 2, this one, 2FFD, صح? So the 22 is going to be stored here. If I want to store it here, I just replace this offset with a 0. If I want to store it afterwards, I increase the offset. Okay, so we use an index register plus an offset. The offset here is a number. This number can be 5-bit. And when it's 5-bit, يعني we're talking an أرقام from minus 15, minus 16 to plus 15, right? When we're talking about 9-bit, we're talking about numbers from minus 256 to plus 255. When we're talking about, and I'm not going to repeat them, they're here. They're here, 9-bit or 16-bit. 16 from minus 32K to plus 32K. ماشي? So the same concept. You load and store. What is the benefit of using an index register? To point to a memory location and you tell it, I want to load somewhere, load contents from a memory location that X or Y is pointing to. What could be behind that? How can we benefit from that?
If we are working with a table somehow, or
yeah, if you want to do something repeatedly, right, and keep doing the thing over and over again 100 times for the next 100 locations, مثلا. So you can have an instruction to load, then you increment X. Next time you come back to the load, X will be pointing one location forward, right? So plus the offset, so you moved one location forward, right? So you can move 100 times and do the same operation. Instead of repeating it 100 times, you can put it in a loop that repeats 100 times, incrementing the pointer. In this case, the index register is the pointer in every loop. Okay? Rest of the stuff, similar to what we did. Yani load D. D is 16-bit, right? D is 16-bit. So I'm gonna load data from 2 memory locations. So if we go back to our board, so this example, for example, load D 10, comma, X, it was, let's say X. If X was مثلا 1000, 10 here is decimal, right? If I put a $sign here, the number is completely different. It becomes like 16 decimal. Right. So, and D is 16-bit. So I want to load 16-bit. While this memory location 1000 only holds 8-bit. So if this is memory location 1000, and X points here, right, plus 10, so we're talking about memory location what? 100A, right?
A, yeah.
Then 10, then a hex, if you convert to hex, it's $. So I want to load what's in here into D, but D is 16-bit. So I load D high with the contents of memory location 100A, right? And D low comes following the big Indian convention is the following location, which is 100B. So what's in here will come into memory location 100B will go into D low, right? So if we had a number here, 1, 2, here 3, 4, then D will become after the load $1, 2, 3, 4. Okay. طيب, following the same example, I'll do a load accumulator A. What was it? 10, comma, X. What will be the semicolon here is means a comment. What will come into A? The 1, 2, right? While
8-bit بس.
عفوا
8-bit بحكي بس.
Yes, 8-bit. While if I want the 3, 4, what can I do? Just increment the offset, right? So in this case, A will be 3, 4. تمام clear. طيب. Hope this is clear. Now for the 9-bit, the same, exactly the same, but instead of the offset, instead of if being 5-bit, يعني a number from -16 to +15, it can be a 9-bit number from -256 to +255. That's it. That's the only difference. Okay. And you can use any of these index registers, X, Y, stack pointer, program counter. And with a 16-bit address, offset, sorry, also you can provide a 16-bit offset. And I assume here, by mistake, the $sign is dropped. Well, yeah. Well, 2000 still fits within the 16-bit 64K, even if it's not text. طيب. Okay, so the offset can be a number from 5-bit to 16-bit. Also, the offset in this addressing mode, yani on the right, we use an index register always, X, Y, or stack pointer or program counter. The offset also can be an accumulator. طيب, يعني register A or B, or even D for 16-bit. Same thing, instead of putting here a number 5, you can put the 5 in B first, then use B. Okay, same thing. So what will be loaded to accumulator A here? The contents of the memory location that is pointed to by X plus B. Okay. Yani if B was 2, X was 1000, then well, we just add them. Then the memory location contents of 1002 will be loaded to A. 1002. What's in here will go to A. B, and here you're going to load 8-bit. Here you're going to store 8-bit. Load Y. Y is 16-bit. You can load Y with the contents of memory location that is pointed to by X plus D. D in this case 16-bit plus 16-bit, you get a 16-bit address. بالنهاية, you're pointing to an address. Okay, this is the address X plus D. Okay, you're gonna load to Y. Y is 16-bit, so you load this part to Y high and this byte to Y low. Clear? Should I move faster? Yes.
سؤال بس ممكن.
Yes, sure.
هلا لما بحكي عن البي والدي هون والاي، بحكي عن الفاليو اللي مخزن باي وبي ودي ولا
exactly. Yes.
مش كادرس كلوكيشن؟
No. As a number instead of the offset.
Yes.
Just a number. يعني assume B is 2, you just add 2. You just add 2. You don't go to a memory location address 2 and no. That it's the offset.
تمام.
Okay.
دكتور والنمبر دائما بالهيك صح؟
النمبر in this case, well, the number is a number. يعني B, if B, at the end of the day, B is a binary number 00000010. It is 2 in hex or decimal, but if it's and here like this, if you want to, and everything is 0, then it is 16 in decimal, but it is a $1 in hexadecimal, right? So it doesn't matter. It is the number inside here. How you want to write it is not important now because you just said the number in D. Okay, the number in D is the same, but when you want to tell anybody about it, you use your expression. You tell him it's 10 decimal or it's a hexadecimal, right? But still, it is still 1010, right? Tamam, everybody? Should I move?
Yeah, tamam.
So this is an example of what I was taught. This is the indirect. This is a new one. Okay. So we just talked about, inherent, immediate, direct with the extended option, relative, indexed. Indexed we saw with an offset, a direct number offset constant. We saw that we can use accumulators A, B, or D. Now, both A and B here, these two cases, could be used with a pre-decrement, pre-increment, post-decrement, post-increment, before going to the indirect addressing mode. Let me tell you what is a pre-increment, pre-decrement, post-increment, post-decrement. Are there any examples here? Why is it not here? Index, then here is the accumulator. High auto. Okay, I'll leave it till we get to here. ماشي. Auto decrement, auto increment, pre and post. I'll come to it later. But for now, okay, so we're using an offset that could be a constant or an accumulator with an index register. Add them together, that's your address where you get your operand. Okay, the offset can be is a signed number. Can be positive, that means any address after the offset, the index, or before the index. Okay, a new addressing mode is the indirect indexed addressing mode. In this case, you provide an address where the address of the operand is at. Yani, in this case, we use brackets like these. See these brackets? This means x plus 10. If x was 1000 and 10 decimal, yani a hexadecimal, then 100A, صح? Yani, if x was 1000, then this is an address, 1000 plus 10, which is 100A, صح? Here, the offset plus x. 100A is a location, فيه هذا number, 100B is a location, has 00. We don't get the 2000 is not our operand. This is not what we're gonna send to A. This is not what we're gonna send to load to A. This is the address where the operand is at. So we go get, if we use the brackets, then what's inside here is an address. The sum of these two will result in an address. The address 16 bits. So we look at two locations, 100A and 100B. We get a number. What is this number? 2000. Okay. This is our new address. We go to address 2000. What do we have here? 40. This is what we are going to send to A. So what's A going to be here? So we say load accumulator A 10 comma x, x 1000. Then A is going to be 40 hex. 40 hex. Yani if we go to our board and compare. So let's assume x equals address 1000. And we say load accumulator A. 2 comma x without the brackets. This means that we are going to go to memory location. the address here, the effective address that we're going to deal with is x plus 2, يعني 1002. So we go to 1002, get the number in here, مثلا FF, okay, get this number, send it to accumulator A. However, if we say load accumulator A with, we use the brackets 2 plus X, close the bracket, then our address here that we're going to fetch our operand from is the memory location, okay, where the contents of the memory location of 1002 is pointing to. يعني 1002 is FF. This is not enough for an address. We know the brackets means what's inside here is an address. It's not the operand. 1002, we go get 16-bit, not 8-bit. So FF, and here let's say in the following address 1003 was a number مثلا 12. So our new address is $FF12. So we go to memory location $FF12, we get what's in here and send it to A. مثلا here was $01. So A will be 01. Is that clear?
يعني زي ما بدأ immediate والdirect تقريبا.
Well, the immediate was a number right after the mnemonic. The direct, the address we're going to fetch the address of the memory location was also directly after the mnemonic. Here, يعني this is like the direct, but indexed, يعني you can add a number, but this one, no, it's completely different. You're saying, I'm giving you an address in the memory location. You go there, you find another address of a memory location, you get your operand from. So you go to memory twice here, in this case, when you use the bracket. Here, the address, this is the address of the data, being Gaussian operand, that you're gonna load. But in this case, this is the address of the address of the data, which is the operand. That's why it's indirect. I point you to a place where you can find the address of the place where you're going to get your data from. So I pointed you twice.
Yes, yes, no.
Okay. يا الربع. Any questions?
أنا دكتور عندي سؤال.
تفضل عمر.
سؤال بسيط بس بالنسبة لو بدي أروح على memory location أطلع جواته الأدرس وبعدين الأدرس اللي جوا أروح عليه أدخل الفاليو في A بس بدون ما أعمل shift للأدرس يعني بيكون السنتكس إنه بس بدون الرقم اللي قبل الإكس مثلا ولا كيف السنتكس بيكون؟
So again, let me try to understand your question. You want to load, this is a memory location. Address مثلا 1000.
Exactly. ومثلا في أدرس 1000F مثلا.
طيب 100F. طيب what do you want to load to A?
اللي جوا 1000F.
This one.
Exactly. فراح يكون الادرس 1000 اف موجود في الميموري لوكيشن 1000.
And you want this address to be here.
Exactly.
0F in 1001. So you say that you do it like this. Load accumulator A ماشي of the memory. طبعا first you make X point to address 1000 ماشي.
Yes.
And you do this 0, X and use the bracket.
Exactly. That's
X
my
is
question.
1000. X is 1000 plus 0 is 1000. So, but since we're using a bracket, so we're going to go get from two locations, 1000 and the one following it, a 16-bit number, which is in this case 100F. And this is our address, okay, where we're going to get what's inside here. مثلا, inside here is AA, and we send it to accumulator A. So we use the brackets, answering your question.
And we also use the 0. We cannot omit the 0 from the brackets.
Oh yeah, you have to use an offset. You have to have in this addressing mode. Yes, you have to have an offset. Okay, you have to have an offset next to with the index register. Yes, and this offset can be any number, 5-bit, 9-bit, or 16-bit. Yes. Okay. Glad it's clear. Accumulator D, indirect index, just exactly the same here. Instead of using within the brackets, instead of using a constant offset, you can just use D method. Okay, this is the other addressing mode. You just method load accumulator. Well, load X. Well, load X. Yes, yeah, X. Bracket D, comma, instead of constant offset, comma Y. Y is our index register. Okay. So here, if Y was 1000, D was 0001, then we're gonna go to address 1001, 1001 and 1002. Get the 16-bit address here. That is maybe AABB. Okay. $AABB. Get the operand inside here, and I'm loading X, so I'm loading 16-bit. So we go get AABB and AABC. So let's assume here we have 1, 2, 3, 4 hexadecimal. So X will be, after this instruction is executed, $1, 2, 3, 4. اوكي
دكتور بس سؤال صغير. هلا هون حكيت الواي ايكوال $1000 انه هذا الادرس للواي، بس الدي الدي الفاليو مش الادرس الدي.
But you add it to y. You add it to y. It's a value. It's a 1. You just added 1 to y.
طب اوكي هلا مرات بتحكي y ايكوال دي ايكوال، كيف اميز انه هون هذا ادرس وهذا فاليو لهذا
depending on how you use it. So in this case, X, I loaded X. X is just a register. Say I load D مثلا. Okay, يعني these are just numbers here. But how you use them at the end, the result of adding these two is going to be used as an address.
Okay, بس الفكرة إنه الدي لما أنا أكتب D equal 0001.
Well, there is no instruction, Mustafa, that is such like D equal, and I'm just assuming, and if I want to do this, if I want to load D with 1, I say load D with immediately number 0001 إذا I want to do it in assembly, and I'm just assuming here.
يس انا الفكره انه هاي الدي انا كفاليو باخذ الكونتنت اللي بدي بعمل له بجمعه للادرس اللي ادرس واي.
Exactly.
وبعمل لود.
The result is an address. Yes.
Yes. Okay.
Okay. So we're talking about assembly again. So you guys, please, there is no such instruction in assembly that y equals dy. I'm just giving this is a short of previous instructions that already loaded y with 1000 and loaded d with 1. Okay. The kind of instruction given here or example given here, it's again indirect addressing mode, indexed addressing mode. In this case, the index register here used is the program counter instead of X. And remember, where does the program counter point? It always points to program memory. So look at this jump instruction. So jump, the jump will send the program counter to a memory location depending on D, And if D was 0, after executing this instruction, where is my program counter pointing? طبعا you all studied assembly, so you all know that these are called directives. These are not instructions. Okay, but you just define something called target 1 at go 1, whatever. We're going to talk about directives later. So the program counter usually points to the instruction, the machine code that follows the current instruction being executed, which is here. So already the program counter is pointing here. After finishing the jump, you're saying jump to an address. What is the address? The address is at a memory location, which is the value of the program counter plus D. If D is 0, the program counter is here. So high program counter. He's assuming this is the first instruction. The program counter is here. So my value, you'll find the place where I'm going to jump to here. If D was 1, I'm going to add the contents of the program counter that is pointing here plus 1, here. You get this address as your new target of program counter. If D was 2, then this is your address where you're going to make the program counter go. This is something good, if you have previous instructions that set D based on conditions, okay, then you're going to jump, just like select in C. What was that instruction? You select, is it a select? If it's not a select, is it a select? If something is 0, just like a lookup table, if this is 0, you go here. If it's 1, you go here. If it's 2, you go here. But as a concept, we're looking at this part. This is an address in the indexed indirect. You compute the effective address by adding these 2 registers. You go to a place, the place over there, you find your effective address where you're gonna use with this instruction, the jump in this case, the load in this case. The directives here, we're gonna talk about them, but these are not instructions. Auto, pre, post, decrement, increment, indexed addressing. Let me go to our board and try to explain it. Auto increment, auto decrement, pre or post. Pre or post. Let's look at this. In our previous examples, in the index addressing mode, we said load accumulator A with 1, X. What does this instruction do? يا جماعة.
Go to address x plus 1.
يعني let's assume إنه x is 1000. So this is gonna load from address 1000. So if x is pointing here, I'm gonna go load from address 1001. What's in here? What's in here, and send it to A. تمام. Now with the blue pin, same instruction, but if I use a -1, this was a +1 يعني صح? A -1 would do what? You will go
0
to x -1, so to address 0 f. You go get what's in here and send it to A. تمام. So I use the sign with the offset. I use a sign with the offset to say that this offset is positive, yani downwards, or negative upwards. Is that clear?
Yes.
Now I'm gonna start using signs with the index register. Yani load accumulator A 1, x. And x here, I'm gonna put a plus after the x. This case, the 1 is not an offset anymore. This is not an offset anymore. This is an increment value. طيب. If this was a minus, then this would be a decrement value. If the plus or minus was after the x, then this is a post increment or post decrement. If the plus or minus were before the index register, then we call this is a pre-increment for the plus or pre-decrement for the minus. Example. Load accumulator A 1, x plus. What would this do? First, it will go to memory location that is pointed to by x. So memory location that is x is pointing to, and bring it to accumulator A. Then it will go to x and increment it by 1. So x will point to the following memory location. ماشي? The result of this load is two things. You're changing the value of register A by loading contents of memory location that x is pointing to. Then after the load, you make x point to the following location. A post increment. So post yani after loading, post the load, you increment x by 1. If this was 2, then we add 2 to x. يعني we jump 2 locations.
بس انا غيرت اللوكيشن لاكس بلس 1 بس كلوكيشن اكس.
Yes. We change the location where x is pointing at after the load. يعني what we loaded was the original location where x was pointing at. Okay. So if we had a 1, 2 here, A will be 1, 2. طيب. Let's do something like this. Load accumulator B 2, minus x. يعني the sign being after the index register or before the index register, this makes a lot of difference. يعني this is a pre. In this case, it was a post. So we incremented X by 1 after loading the memory. ماشي. Here we decrement before. يعني here what's going to happen is that
X minus 2
is going to become X minus 2. Then the new X, where it's pointing, we load the content to register B. So يعني in this case, I memory location. This is X pointing here. X. So first you're gonna make X minus 2, 1, 2, make it point here. This is the X. ماشي, the new X. Load what's in here to register B. A pre-decrement. If this was a plus, I make X point 2 locations afterwards here and get this to send it to B. Yani if the load accumulator B was like this, مثلا 1, comma, plus X, then having the sign before the index register, then the first thing you do is increment or decrement the index register. So X will be incremented by 1, لأنه this is the increment value. Then you go get the memory location of the where the new X is pointing at and store it at B in this case. What decides that I increment or decrement first, then get the memory location? The decision should be based on this sign. Is it before the index register or after it? And in this case, the number here is not an offset anymore, okay? It's not an offset. It is an increment value or decrement value.
بس لو حطينا كواس بيعطيني ايرور ولا في
No, it doesn't accept in there is it doesn't accept it. Yeah, you'll get an error, yes. Okay.
Doctor,
now
and here the sorry.
Yes.
And
sure.
the number what we were call it offset. Now it's not offset. This is I assume it's positive number. It will not be again negative.
It can be from
negative.
It can be from minus. Well, into you're incrementing or decrementing, right? So it's a number from 1 to 8. Yani from 1 to 8. Yeah, where is this thing? This number can be any number from 1 to 8. Best positive number. If you put a minus here, you subtract it. If you put a plus, you add it. Okay. So yani effectively you can decrement or increment from -8 to +8, صح? So this is a 3-bit number. 4-bit. -8 to +8. But you don't put a sign next to it. ماشي?
Okay.
Okay, and the index register here is again X, Y, and stack pointer. The program counter is not part of it. Yani, with the pre, post, increment, decrement, these are the 3 registers you can use. Okay. Now look at these. Does anybody remember? Most of you said you learned in your undergrad the Intel, right? Processor, 8086 or 8085. So you used to deal with a stack. Those who dealt with PIC, there is a stack, but it's a hardware stack. You didn't have instructions to push or pull from it. Anyways, when we go learn about the stack, there is always something called stack pointer pointing to the top of stack. If you want to store into the stack, you use an instruction called push مثلا X. So you go X 16-bit, you reserve 2 locations and make the stack pointer point to the top of the stack. Whenever you say load Y, مش load Y, sorry, pull. In Intel they call it pop, P-O-P. And here we say pull X. Pull X means go get whatever the stack pointer is pointing at and store it into X. ماشي. After you load it, the new top of stack is not this. This is the new top of stack. The stack pointer needs to decrement. So this instruction, load X with 2 comma plus stack pointer, pre-increment stack pointer by 2, then load. Increment يعني go down, صح? Go down. Then load. You load this. Pre-increment. This is a post increment. After you're done, you post increment. I don't want, okay, I don't know, should I talk about this now? For real quick, for those who are familiar with this thing, it doesn't hurt. So if I have a stack pointer pointing here, ماشي, if I want to pull to X, pull X just like that, that means I want to get these two locations and send them to X, then makes the stack pointer new value point here. So then this is the new top of stack. So you can think of if this pull X is broke, you cannot use it. You can use an instruction like load X with these things, then make stack pointer go here to this location, right? So after you load, so you increment, so a post increment, so stack pointer post 2, right? Post. So this will go to memory location. This location, step number 1, you go to memory location where the stack pointer is pointing at, you load it. Well, memory location that stack pointer plus 1 is pointing at, and memory location where the stack pointer is pointing at, and 2 locations, and you send them to X 16-bit. Afterwards, the stack pointer will be incremented. Stack pointer will be incremented by 2. So you make it point to the new top stack. Anyways, we don't know what is a pull yet. Later on, but this is an example. Just take it like that. But there is an equivalent of it if you use a stack pointer. Right. I think we're done with the addressing modes. So if we go back to this table, I think we covered everything. We covered everything. So we use these with the post and pre-increment decrement. And we use the indirect index addressing mode with a 16-bit offset or accumulator offset. We're done with the addressing modes. Any questions so far? All good? Some instructions. Would you like to start using, should we start instructions, or is it clear when I say load and explain, load accumulator A مثلا and explain it to you, and store مثلا? Is that enough to go build on an example?
Yes, Doctor.
Should we go use CodeWarrior and write a small example to add 2 numbers?
Yes,
and
yes,
then,
why not?
And then we come back later to these instructions in more detail.
Yeah.
Let's do it. Okay, Mashi. Let's do it. Did you all install CodeWarrior?
Yes.
Yes.
Yes. So, and I meant not to use it before I installed it, just like you guys. So you all go with the same experience. By the way, make sure you load it. Yes. Oh, never mind. Okay. So the first thing you do, you create a new project if you get this wizard. If you don't, you go to project, a new project. Should I start from here or go to the menu? What do you prefer? Let me go to the menu. Okay, you installed CodeWarrior project. Oops, file, project. Where is the? Well, why isn't it? Type. Let's start with again. What if we don't get this display on startup? Create a new project. Type. Okay, keep it. Create new project.
من فايل بيطلع اللي هو open الستارت dialog.
والله file.
Start dialog.
New project here. Or the start the dialog or new project. Okay. Okay, guys. I'm closing it again. Cancel. Run CodeWarrior. Oops, I close it. Run CodeWarrior. Close this one if you don't want it. Close the tip if you don't want it. File, a new project. Okay, new project. Now, the first thing you do is pick our microcontroller. Our microcontroller is an HCS12. Mashi. So you go to the next choice, HCS12. You go to the, what is our family member? DP or DG. HCS12D family. Mashi. D. How do I know? Do you remember how do I know?
Yes, دكتور من الاسم.
Yeah, we had the name, right? We had it in one slide before in the book. Okay.
Yes.
Okay. Now, there is a DP or DG. Both work with us. Some slight differences. So we'll pick the DP. DP or DG? Well, we have both.
هي تحت دكتور دي بي 256 موجودة.
DP. Ours is DP, right?
256.
Ours is DP.
يس دكتور من الداتا شيت اللي اعطتنا اياها.
DP صح؟
DP 256.
In the data sheet, yes, again, here's the data sheet, just to confirm. Where is the data sheet? Here is it. And here's the data sheet for the whole thing, 250 DP here. 256 DP. And if any of you got the, where do I have a light? If you already got, how do I turn the light? If you already got, this okay. My chip, if you already got the microcontroller from the lab, you can, did everybody get it or not yet?
بلا دكتور خدناها.
طيب. When you get the board, let me stop sharing for a second just to show you the board. We're gonna use it more later and give more more details about it. Do you see my picture large?
Yes.
Okay, so this is the board, ماشي, and this is a breadboard. We can just take it out. A breadboard just to prototype some circuits. It's not part of the board actually. And if you look at this chip here, there is something written on it. شايفين شو written on it? DG, the same number بس DG. شايفينه معكوس ولا؟
لا هيك بينت دي جي 256. Yes.
200 DG. But anyways, for this from experience, DG or DP both work. The differences are very slight.
Yeah, my board is DG as well.
DG. So we can pick the DG خلاص to be exactly the same. ماشي. Oops. Okay. I always have my another device on 4G on in case something happens to the internet. Okay, back to CodeWarrior. But the data sheet will do it, the same data sheet. And we did not go through this data sheet together yet, right? We didn't. And DP or DG 256. Okay, so we go to DG 256. 256 is the flash memory, okay, guys? The flash memory size, the program memory size. We know we cannot access it at once, 16K at a time, but it's there. Full chip simulation. Next. Okay, what in this project, what code we're gonna write? C, C++, relocatable assembly, absolute assembly. What code are we gonna write? Right now, we're gonna start with assembly. Later on, once we're good in assembly, we're gonna start move and work in C to do things faster. In one of your lab assignments, you're gonna work with C and assembly. You're gonna write you do something with some pieces of the project done in assembly and some pieces done in C, and you're gonna be able to transfer and share things between the C file and the assembly file to generate an executable. Right now, we're gonna use assembly. Okay, what assembly are we gonna use? A relocatable assembly or absolute assembly? Relocatable assembly supports to split up the application into multiple assembly source files. The source files are linked together using the linker, and in this case, even the memory addresses are relocatable. So the assembler may relocate things. You say, I want to reserve a memory location here. It may be relocated if it's wrong, or it will affect something else. Okay. At this stage, we know what we're going to do. We're going to deal with the very low level details of the memory. So we're going to use the absolute assembly. So this we're going to use the absolute assembly. The memory addresses, locations we're going to provide are the ones we want to work in. Okay, where do I want to save my project? So let me choose a location. Let me choose my C drive. Create a folder here. Okay. Embedded systems design. Class demos. Spring 2021. And here, let's make the folder for project 1. So class demo 1. Okay. You can name it, but since it's in a named folder, I can keep it. MCP is a project file name. Save. Next. If I want to add other projects, other files from that I previously did, I can add them. Next. Do you want this development environment to add to the code, the project, any initialization code for some devices initially, device initializations, etc.? No, I don't. I want to do everything myself. No. Finish. And this is what we get. Okay. We get under sources our main.asm file. When we write C, we're going to get main.c. In assembly, main.asm. And this is the project. Okay. The derivative here, .include, points to the DG256.include, which is this one. This one is added as an include header file because we picked it in the wizard. And this is done for the family member we picked, okay? And in here, see where the E square prom start, equate, for address 400, E square rom prom ends at address FEF. In a different family number, these numbers may vary or be different. The read-only memory 4000 start, at address 4000 start. This is the flash memory, our program here. When we write our program, we're going to start at address 4000, okay, and end at address 7FFF. We'll come to these addresses later and look into the data sheet. Another place, C000 or C00 end. Why this or this? Depending, we can choose to move our program location pages, memory location pages, P page. Then every register inside the code, port B, مثلا, port AB, port AB is the AB register, and these are masks to enable you to point to a bit. Port A, for example, at address location 0, port B, address location 1. Okay, if you remember when we talked about registers, we said there are CPU registers and I/O registers. Port A, port B are I/O registers, and they are treated as memory locations. Here, this port B is going to be memory location 1 in the memory. طيب. DDR, DDR-A, DDR-B, all the registers we're going to deal with later on in our coming chapters covering serial communication, analog digital conversion, the parallel ports, whatever. All here, this include file has all the definitions of their locations. It is different from a family member to another. ماشي. ماشي. So let's go back to our main.asm. When you first create your first program, okay, it's 6:15. You get an example here. The example code written here, there is a code written here already, which is the Fibonacci series, something to calculate the Fibonacci numbers in the Fibonacci series, okay? And the code, here's the main loop, and okay, next time, we're going to continue from here. I'm going to go, it's saved now, file, save the project, or if you compile it, hide, float. So if you go build the project here, you're going to build, look for assembly errors or whatever, link, it's saved. ماشي. Simulation, these are the registers, memory locations we're going to deal with. Next time, we're going to write our code here and single step through the program, look at everything. And then we'll do something physical, maybe turn on an LED and run it, the same code on the microcontroller. Next time, inshallah. So let me end the recording. If you have questions, you can stay until after I stop it. Stop share, stop record. Okay, see you next time, Monday. Remember to solve the problems and turn them in on time next Wednesday. And we may have on the next Wednesday a quiz or any next Wednesday or after. Thank you very much.